This is the 23rd video in a series on ordinary differential equations. And for the past two videos, we've looked at linear systems of differential equations. And so far, we've been able to solve the differential equation y prime equals a times y, where these are both vector valued functions and a is an n by n matrix, if all of the eigenvalues are real and the eigenvectors span Rn. So we can completely solve this sort of system in that setup, and that's based off the fact that really A is diagonalizable there. We were also able to solve the non-diagonalizable case just for very special subcases. So I'll let you guys check out video 21 where we do this and video 22 where we do this if you haven't done so already. But that leaves one remaining case, and that is, what about if we have complex eigenvalues? So when I say diagonalizable over here, what I really mean is diagonalizable over the real numbers. And that's because that allows us to only use real valued functions. Whereas if we diagonalize over the complex numbers, we have to use complex valued functions, which is definitely allowed, but we're trying to stay away from those as much as possible here. Okay, so we're going to start with this kind of leading example. We'll first show that this indeed has complex eigenvectors and eigenvalues, and then we'll hack our way to a solution and see how that solution somehow ties in with those eigenvectors and eigenvalues. Okay, so let's first look for our eigenvalues of this matrix. So remember, that means we need to look at the characteristic polynomial, which I'll denote by P sub A of x. So that's going to be the determinant of x times the identity matrix minus A, or sometimes A minus x times the identity matrix. It's pretty much the same thing. Okay, so this is going to give us the determinant of x minus 5, 4 will go here, negative 10 will go here, and x minus 1 will go here. Okay, so that's good. So now let's see what we get. We'll get x minus 5 times x minus 1. That's x squared minus 6x plus 5, and then plus 40. That's from 4 times negative 10, but then we're subtracting that. So let's see. That means our P sub A of x is x squared minus 6x plus 45. So we'd like to find the roots of this polynomial, and those will be exactly our eigenvalues. Okay, well, we'll go ahead and use the quadratic formula here because you can check very quickly that this doesn't factor over real numbers. And so that means we'll have lambda is equal to, I'm calling lambda the roots, as that's the standard notation for eigenvalues. So lambda will be, let's see, we've got negative b, so that's 6 plus minus the square root of b squared minus 4ac. So that ends up being 36 minus 4 times 45. So I'll write that, 36 minus 4 times 45, and this is all over 2 times a, in other words, just the number 2. Okay, so I'll let everyone simplify this on their own, but what you end up with is 3 plus or minus 6 times I. So that means we've got our two eigenvalues, but they're complex conjugate pairs of each other. Now from here, we'd like to calculate one of the eigenvectors. And luckily in this case, if we calculate one of the eigenvectors, we have both eigenvectors, because they'll also be complex conjugate pairs of each other. So let's maybe calculate the eigenvector corresponding to 3 plus 6i, and then we'll get the other one for free. Okay, so that means we need to look at the null space of 3 plus 6i minus a. So what does that end up being? We'll have minus 2 plus 6i goes in this entry. We'll have a 4 in this entry. Notice I'm just replacing x with 3 plus 6i. We'll have negative 10 in this entry. And then in this entry down here, we'll have, let's see, 2 plus 6i. So something like that. And now let's simplify this matrix by doing some row operations so we can easily see the null space. So my first row operation will be to take row 1 and replace it with 2 plus 6i times row 1. In other words, I'm just scaling row 1 by 2 plus 6i. The motivation for that is I'd like to get the complex numbers in our second column. That way we can combine everything a little bit more easily. Okay, so we'll have the null space of, I'll copy my second row down, so that'll be negative 10, 2 plus 6i. And then what will be in my first row? Well, you can check that 2 plus 6i times negative 2 plus 6i is negative 40. That's because we've got this negative 4 minus 36, and there's no cross terms because we've got something that's like a difference of squares, but it's involving I, or the imaginary number here. Okay, so here we've got negative 40. And then the easiest way to write this next term is just 4 times 2 plus 6i. But check it out, this first row is a multiple of the second row. That means that we can multiply the second row by 4 and subtract it from the first row, and then we've wiped out one of those rows. So let's maybe wipe out the first row using that method and then swap the second row up to the first row, and simultaneously we'll divide the new first row, the old second row, by 2. So after all those, we'll now be looking at the null space of negative 5, and then 1 plus 3i, and then 0, 0. Okay, so that's good. And now let's see that that will correspond to the following system of equations. We'll have minus 5x1 plus 1 plus 3i times x2 equals 0. And that's just by taking this matrix and multiplying it by the vector x1, x2, where that vector x1, x2 is in the null space. But now moving some things around and solving for x1 and x2, you can see that our eigenvector, which I'll write as v1 maybe, which is x1, x2, can be taken to be 1 plus 1, 5, and then plus I times 3, 0. And that's just by choosing the appropriate value of the free variable. Notice that we can take x1 or x2 to be free in this case. So here we're perhaps taking x2 to be equal to 5, and then that forces the value of x1 to be 1 plus 3i. So just to reiterate, the eigenvector associated to eigenvalue 3 plus 6i is equal to 1, 5 plus I, 3, 0. And that means that the eigenvector associated to 3 minus 6i will be exactly the same with a minus sign there. That being said, since those eigenvectors do not span Rn, because they're not even real vectors, that means we can't use this first result. We also can't use this second result because it is indeed diagonalizable, just not over the real numbers. And we'll first find our solution just by hacking together some previous knowledge and then compare that to what we found out about the eigenvectors and eigenvalues. Okay, so let's do that. So far, we've explored exactly why this example doesn't fit any of our solution methods so far, and we did that by finding the eigenvectors and eigenvalues and showing they came in complex conjugate pairs. And now we'll find a solution to this using some means that are not quite very efficient, but they will shed some light on more efficient strategies down the line. So let's take this matrix vector differential equation and turn it into a system of differential equations. So we'll have y1 equal to, or y1 prime equals 5y1 minus 4y2. And that's of course making the vector valued function y be y1, y2 as the components. Okay. Furthermore, we'll have y2 prime is equal to 10y1 plus y2. And now from here, we'll introduce some notation. So let's set y equal to y1. And if you recall, we've been doing a lot of stuff in these previous two videos where we went over these techniques, talking about the rank order duality for differential equations. So since this is a system of two differential equations, perhaps we can turn it into a second order differential equation. And that means we'd probably like to look at y double prime. But let's notice that y double prime is the derivative of y prime, or in this case, the derivative of y1 prime. But we know that y1 prime can be expressed with y1 and y2 as follows. So that means we have y double prime is 5y1 prime minus 4y2 prime. Just essentially by taking the derivative of this first of our two equations. Okay, but we'd like to rewrite this so that it only has to do with y. Notice that this one right here is immediately just y prime, so that's lucky. But that means we need to take care of the y2 prime. And we can in fact do that using the fact that y2 prime is exactly involved in this second equation. So that is 10y1, I'll just call that 10y, and then plus y2. So let's see where we are so far. We have y double prime is equal to 5 times y prime, and then we'll have minus 40 times y, and then minus 4 times y2. And that's by doing this rewriting, which is given by the purple overline and that green box. Now, what do we do with this y2? We'd like to write it all the way in terms of y1. But luckily, we can do that with this first equation. We can take this minus 4y2 and rewrite it as 5y1 minus y1 prime. In other words, so this will be equal to y prime minus 5y. And that's just by solving this first equation for y2, keeping in mind that y1 is equal to y. But now we can start putting some things together. We have 5y prime plus y prime. That'll give us 6y prime. And then we've got negative 40y minus 5y. That'll give us negative 45y. But that means that we can move everything over to put it in a more standard form, and we'll have y double prime minus 6y prime plus 45y equals 0. But that has a corresponding polynomial, and that corresponding polynomial is x squared minus, or r squared minus 6r plus 45 equals 0, which has roots, well, you guessed it, it's 3 plus or minus 6i. So 3 plus minus 6i. But putting all that together, along with our techniques from solving second order linear differential equations with constant coefficients, we know that our solution is y equals e to the 3t times c1 cosine 6t plus c2 sine 6t. Great. But remember, that's not just y, that is in fact y1 from our original substitution. Okay, so now that we have that, let's maybe bring this version of y1 up, and then we'll determine y2. And after determining y2, we'll hopefully be able to put this together. So not only does it involve the eigenvalue, but it also somehow involves this eigenvector. So here's where we left off. We took our matrix vector differential equation, turned it into a system of differential equations, did some trickery to solve for y1 by turning this into a second order differential equation. But then, using the fact that y2 can be expressed with y1 prime and y1 by this first equation, we can also find y2. So I did that off the board, but that's just a straightforward calculation. And now we'd like to determine the shape of our solution, which is this vector valued function y, which is made up of the components y1 and y2. So I'm going to put this together into e to the t or e to the 3t cosine terms and e to the 3t sine terms. So let's see. first off, I'll have e to the 3t and then cosine of 6t. And now let's see what vector is multiplied to this, or what direction this function is pointing in. So let's see, for y1, our coefficient is c1. And for y2, our coefficient is 1/2 c1 plus 3/2 c2. Okay, now we'll do the same thing for the sine part. So we'll have plus e to the 3t sine 6t. And then that'll be in the direction of, let's see, we'll have c2 and then 3/2 c1 plus 1/2 c2. Okay, so this would be the solution in vector form. But we're not really quite done, because we'd like to somehow relate that to not only the eigenvalue, which I think it's already related to the eigenvalue given that we have this e to the 3t, this cosine and sine 6t, but we'd also like to relate it to the pair of eigenvectors. So how can we do that? Well, we'll do that by taking special values of c1 and c2 and getting two linearly independent solutions that are expressed with the real and imaginary parts of this vector. So let's do that. So let's start with the following substitution. We'll take c1 equal to 1 and c2 equal to -3. And that'll give us vector y1. I'm misusing notation a little here. I'm using y1 again, but now it's like a vector valued function y1. It's our first solution, if you will. And this ends up being e to the 3t cosine of 6t, but now this is in the direction of 1, 5. Oh, but check it out. This 1, 5 is exactly the real part of our eigenvector. Okay, and then we'll have plus e to the 3t sine of 6t, and that will be in the direction of 3, 0. But notice that 3, 0, or actually that's -3, 0. But notice that -3, 0 is in the direction it's parallel to this second portion here. In fact, if we pulled this minus sign out and put the minus sign here, then we'd have exactly the imaginary part of that second component. And that's in fact how we'd like to write this. Okay, so that would be for that choice of C1 and C2. And now let's see what we could get for another choice of C1 and C2. And here we'll take C1 equal to 3 and then C2 equal to 1. So it's like kind of the dual of what we just saw, except we don't have a minus sign in this case. Okay, so that's going to give us another solution, which I'll call y2 vector. So we'll have e to the 3t cosine of 6t. And now this is in the direction of 3, 0. And then we'll have plus e to the 3t sine of 6t. And this is in the direction of 1, 5. So you can check pretty easily that these are linearly independent solutions. I'll let you do that. But let's notice that this first solution has the 1, 5, which is the real part of our eigenvector attached to the cosine, whereas the second solution has the 1, 5, which is again the real part of our eigenvector attached to the sine, which is in contrast to what's happening with the other term. So notice with this other term, we have 3, 0, and that is the imaginary part of our eigenvector. So I think that's probably enough structure to write down a result which is governing this in general. So here's a somewhat general result governing what we saw in our last example. So let's suppose that lambda plus minus I mu are eigenvalues of A. So these are occurring in a complex conjugate pair. And they also have eigenvectors v plus minus I w. And so that's again the eigenvectors occurring in a complex conjugate pair. Then y1, which is e to the lambda t, times the quantity cosine mu t in the direction of v, the real part, minus sine mu t in the direction of w, the imaginary part of this eigenvector, and y2 is e to the lambda t sine mu t in the direction of v, and plus cosine mu t in the direction of w. So notice the sines and cosines have switched from being attached to the v's and w's. Also, there's a difference of a sign here. So these two are linearly independent solutions of the matrix differential equation y prime equals a times y. So let's notice that this does not only work for 2x2 systems, but also 3x3 systems that happen to have complex conjugate pair eigenvalues, or even larger n by n systems that have these complex conjugate pairs. Okay, so let's look at an example. So we have y prime equals -554, -876, 100, y. So let's calculate the eigenvalues. We maybe won't go through all of the details of calculating the eigenvectors, but maybe we'll do enough to write down a solution using this. Okay, so let's first calculate our characteristic polynomial. So that'll be the determinant of x times the identity matrix minus this matrix. So that'll be x plus 5 minus 4. We'll have 8 here. X minus 7 goes here. -6 goes here. -1, 0, and then -x. So something like that. And now let's do cofactor expansion, but we can take advantage of the fact that this second or this third row has a single 0 in it, so that'll simplify everything. So let's see, let's first go across this first column and this third row. So let's notice that that's attached to a plus sign using the cofactor expansion formula. So we'll have the crosshairs here, which is a -1, times the determinant of the sub matrix. So that'll be -5 minus 4, x minus 7, and -6. Okay, then let's see what's going on for this other bit, which is over here. So that's also going to be attached to a plus sign. So we'll have plus x times the determinant of the submatrix, which is x plus 5, minus 5, 8, and x minus 7. So I won't work out the details. This is just really symbolic arithmetic. But what we'll end up with is PAX is equal to 2 minus x times x squared plus 1. So we have a real eigenvalue, which is 2. I'll call that lambda 1, which is 2. And then we have a complex conjugate pair. I'll call that lambda 2, 3. And that's plus minus I. Okay, now from here we need to calculate the eigenvectors. So I won't go through those details. You do it the same way that we did with this example. And in fact, generally, linear algebra is a prereq for classes like this, so you've probably found eigenvectors before. But what we end up with is V1 is the following vector. So it's 2, 2, 1. So that's the eigenvector associated with lambda 1. In other words, the eigenvalue of 2. And then maybe I'll call these V2, 3. Those are going to come in complex conjugate pairs. Those will be the eigenvectors for lambda 2, 3. So here we'll have 0, -1, 1, plus minus I times 1, 1, 0. Okay, where the plus goes with the plus I and the minus goes with the minus I. Okay, now we can easily write down a system or a collection of 3 linearly independent solutions. So the first one, I'll call it y1 vector, is equal to e to the 2t pointing in the direction of the eigenvector 2, 2, 1. Okay, so that would be maybe the real part of this solution. Well, the whole solution is real, but the one attached to the real eigenvector and eigenvalue. And then we'll have y2 is equal to, well, I'll just write it down and then point out that it's coming from this over here. So it's equal to minus sine of t, and then minus cosine of t, minus sine of t, and then finally cosine of t. So it's that vector. So let's see, we've got sine multiplying into the imaginary part, and we have cosine multiplying into the real part. And so notice that the sine is attached to a minus, which is how those signs are switched. And then finally we'll have y3, which is maybe this version of y2 over here. And that will be equal to the vector function cosine of t, and then we'll have cosine of t minus sine of t, and then finally for the last entry we'll have sine of t. Notice there the cosines are attached to the imaginary vector and the sines are attached to the real vector. Okay, so I'll leave you with a warm-up problem. So a nice warm-up problem built off of all of this stuff would be the following. We've got vector y prime is the matrix 5, -6, 3, -1 times vector y. And that's a good place to stop.